Hello viewers, this is the video lecture for the subject Theory of Computation and for the topic Pumping Lemma for Context-Free Languages. Objectives are to understand the concepts of pumping lemma, to apply pumping lemma for context-free languages. Now let us see what is meant by pumping lemma. Pumping lemma is the theorem or method which is used to check whether a given grammar is context-free or not. And most importantly, it is used to prove that a given language is not context-free language. We can see the problems. First of all, there will be the language a power I, b power j, c power I, d power j. I should be greater than or equal to 1 and j should be greater than or equal to 1. This is our language. And the problem is we have to prove the given language is not CFL. CFL means context-free language. So to prove a given language is not context-free, we have to use the pumping lemma methodology. First of all, we can do this problem in a step-by-step manner. First of all, we have to use the method of proving by contradiction. That is, we will take the assumption like L is context-free. That is, we will assume that the given language is context-free and we will take one example string from our language. Let Z is the string that belongs to our language. So let us take one example string in the format of our language. So we are taking Z equal to a power m, b power n, c power m, d power n. In the second step, we are going to use one important formula from the pumping lemma. So according to our pumping lemma, our string will be equal to u, v, w, x, y. We are going to split the elements from our string with the help of some variables u, v, w, x, y. So we can equate our string. That is, our string is a power m, b power n, c power m, d power n, which is equal to u, v, w, x, y. And in the step 3, we have to use another one important formulation from the pumping lemma. That is u, v, I, w, x, I, y equal to u, v. We are splitting v, I into v in v dot v I power I minus 1. Then we will split xi into x dot xi minus 1. Then when we take the I minus 1 terms into common, so it will be u into vx the whole power I minus 1 dot v dot wxy. This will be the equation number 2. Now we are going to take the we are going to split our string elements corresponding to u, vx, vwx. Now let vwx equal to a power r. We all know our total string is uv will be in the format uvwxy. Now we are taking one portion of our string, that is vwx. This is one portion of our x. We are assuming one portion from our string, that is a power r. Now again we are going to split one portion from the previous portion, that is vx. So vx is one portion of vwx and we are considering our string part a power q for vx. So we all know a power vx is one part of vwx and a power q is one part of ar, which we can imagine one example, that is a power 3 is one portion of a power 5. Similarly, in this manner we have taken the values of vx and again we can take the value for u. U is another one portion of our string. So u is equal to a power, we are taking our another one portion of the string a power p. Now we are going to make the assignments like a power m, b power n, c power m, d power n is equal to, in the right hand side we are going to substitute for the formulation, that is uvwxy. So uv is, u is, for u we have put a power p, then v wx. For vwx we have substituted a power r and simply we have put y in the place of y. So from the equation we have to derive the value for y. So we have rearranged the terms, and for y we are getting the final value a power. After simplifying the values of a, we are getting the value for y equal to a power m minus p minus r, b power m, c power m, d power n. And after that we have to use the second formula for the pumping lemma, that is u into vx power I minus 1 into vwxy. So in this formula we have to apply, first of all we have to apply I value 1. So when we apply I value 1, we have to substitute it in the right hand side, that is u is a power p, vx is actually a power q, I minus 1 means 0. Then we have to apply all the terms for v, w, x and y. For v, w, x we previously derived the value a power r, and for y we got the value in the previous derivation. We have to substitute all the values. After simplifying the value of a, after adding the power values of a, finally we are getting the format a power m, b power n, c power m, d power n, which is the string which has the structure similar to our language structure. So which this string belongs to our language. Now again we have to perform the same derivation by applying I value 2 to the formula u vx power I minus 1 v w x y is equal to our string representations, that is u is a power p, vx is a power q, and I minus 1 means 2 minus 1 power 1. Then vwx is a power r, and the remaining terms belongs to y. After simplification we are getting the string pattern a power q plus m, b power n, c power m, d power n. So this is the string which is not similar to our language pattern. So this string is not belongs to our language. So this leads to contradiction. Hence we can tell the given language is not CFL. And we can see another one problem. For the language L equal to a power n, b power n, c power n, and we have to prove the given language is not context free. So in the first step we will assume the given language is context free, and we are taking on sample string which is called as z, that is we are taking the sample string z equal to a power m, b power m, c power m, and in the second step we have used the pumping lemma formulation, that is our string is equal to u v w x y. That is equation number 1. And in the equation number 3 we will use another one formulation from the pumping lemma, that is decoding pumping lemma in the format of u v I w x I y, that will becomes u into vx power I minus 1 v w x y. Then we will derive the values for, we will split our string into different portions to get the values of vwx, vx, u. So initially we can assume vwx equal to one portion of our string, that is a power r. Then vx is one portion of our string a power q, u is another one sub portion of our string a power p. Then after applying this in the equation number 1, we can get the value for y. This is the last portion of our string, that is we got the value of y. Then we have to apply I value 1 to our second formulation, and we are getting the string pattern a power m, b power m, c power m, which is belong to our language. And in the second step we have to apply I value to our formulation. We have to substitute the values for u, vx power, vx is a power q, power I minus 1 is 1, a power q power 1. Then v wx is a power r, and the remaining terms goes to y. After performing the simplification, we are getting the string format a power q plus m, b m, c m, b power m, c m, c power m. So this is the string which not belongs to our language. That is this string format is something different from our original string format. of our language. So this leads to contradiction, and hence our language is not CFL. In this way, we have to prove a given language is not context-free language. And the possible university questions are: explain pumping lemma and derive its theorem. Prove that the given language is not context-free language. Thank you.